Self-induction. In order to understand what is self-induction, let us consider an experimental arrangement. It consists of a single coil made up of insulated copper wire. It is connected to a source of EMF, battery, along with press key. We know when this key is closed, current flows through the coil, but this current does not rises to its maximum value instantaneously. It increases gradually. We know the current flowing through this coil produces magnetic field. In the magnetic field we can assume magnetic flux. So now let us close this one. Let us see what happens. Look here, magnetic field increasing. So this flux links with the same coil. It links with itself. So this changing flux linking with itself produces EMF in it. This EMF is known as self-induction. This phenomena is known as self-induction. This EMF is known as self-induced EMF. So now if this is opened, then also the current does not decrease to the zero value instantaneously, but it decreases gradually. As current decreases gradually, flux linking with this coil also decreases gradually. This produces EMF once again. So when the circuit is made or broken, there is a change in current. During the change in current, EMF induces in the coil. This is known as self-induced EMF. Now let us repeat the experiment. Now let us open this key. Look here how these lines are decreasing because current is decreasing. This decrease in flux is also change in flux that produces EMF. So now let us let us know what is self-induction. Self-induction is the phenomenon of production of induced EMF in a coil when a current through it changes. Look here, EMF is induced in it when current through the coil changes. If the value of current does not change, EMF does not induce in it. It is not induced in the coil. So the condition for this self-induction is change in current. Of course, in turn, change in flux linking with the same coil. So now, as the switch is closed like this, the current increases from 0 to maximum value gradually, and hence magnetic flux through the coil increases. Flux increases. This change in magnetic flux induces an EMF and current. So this induced current flows in the direction opposite to the direction of the battery current. Look here, this is the current produced by this battery EMF. As EMF is induced, this also produces current, that is called induced current. This current will be opposite to the current produced by the battery. Look here, it is opposite to I, and this opposes increase in current. That is, the current produced by this induced EMF opposes increase in current produced by the battery. So now as the switch is opened, the current decreases from maximum to 0. Of course, it also decreases gradually, maximum to 0 value, and hence magnetic flux through the coil decreases. This change in magnetic flux induces an EMF and current. This induced current flows in the direction of the battery current, which opposes decrease in current. So in both the cases, this induced EMF produces the current so that it opposes increase in current or decrease in current. It means the cause for this induced EMF is increase or decrease. So this EMF tends to produce the current so that it opposes the cause for its generation. Now the self-induced EMF opposes any change. Any change means increase or decrease in the current in a circuit. Hence this EMF is called back EMF. I mean this self-induced EMF is called back EMF. In some books they have written forward EMF also, but there is nothing like forward EMF, it is only back EMF. The self-induced EMF is called back EMF. The self-inductance plays the role of inertia. So here the EMF is induced due to a property of this coil, it is known as self-inductance. That we will discuss next in the next scene. The self-inductance property of this one, this doesn't like the change in current. It plays the role of inertia. Inertia, mechanical inertia doesn't like change in velocity of a body. It means if a body is at rest, this inertia likes that body to be at rest. If body is moving with uniform velocity along a straight line, it likes that body to be keep motion along a straight line. So look here, it is electromagnetic analog of mass in mechanics. So now let us discuss an expression for self-inductance or coefficient of self-induction represented by L. Coefficient of self-induction or self-inductance, of course it is represented by L. Consider the same experimental arrangement. Coil connected to the source of EMF. So here the magnetic flux linked with the coil is proportional to the current through it. Look here, this flux linked with this coil proportional to this current, because this flux is produced by this current. So this can be written as pi is proportional to I. Pi is flux, means number of lines, field lines. I is the current, this current. So pi is equal to L into I. This constant L is known as coefficient of self-induction. Look here, coefficient of self-induction of the coil or self-inductance. Look here, any change in flux sets up an induced EMF in the coil given by E is equal to minus d pi by dt. Of course, this is according to Faraday's law. Faraday's law tells EMF induced is directly proportional to rate of change of flux, this thing, and its negative sign is due to Lenz's law. So EMF E is equal to d pi by dt, but pi is equal to L into I. Substitute for this pi, we get E is equal to minus d into Li by dt, but this L is a constant of this coil. Take this outside like this. So now it is di by dt. Di by dt is nothing but rate of change of current. So therefore E is equal to minus L into di by dt. So using this equation we can define this L, that is coefficient of self-induction. So now consider this equation, E is equal to minus L into di by dt. If di by dt is equal to 1 amp per second, it means the change in current, this current varies at the rate of 1 amp per second. It means in every second its value increases to 1 amp, 1 amp, 1 amp like this. That is 1 amp per second. Then this equation becomes E is equal to minus L into 1. Look at di by dt, 1 by 1 is 1, E is equal to L. It means the value of coefficient of self-inductance, coefficient of self-induction is equal to the value of EMF. Here they are numerically equal. Their units are not equal, they are numerically equal. Therefore we can define L like this, E is equal to minus L, that is self-inductance of the coil is, self-inductance is L, is numerically equal to the induced EMF, this E, set up in the coil due to a unit rate of change of current in it. Look here, once again let me repeat, self-inductance of the coil is numerically equal to the induced EMF set up in the coil due to a unit rate of change of current. It means if current in the coil changes at the rate of 1 ampere per second, then whatever the EMF produced will be equal to, numerically equal to, self-inductance of this coil. So Now let us discuss the SI unit of self inductance is Henry. We already know the SI unit of mutual inductance is also Henry. So now let us define this Henry. So to define this one, once again we have to consider this equation, E is equal to L into di by dt. If di by dt is equal to 1 ampere per second, unit rate of change of current. If this current produces EMF of 1 volt, that is E is equal to 1. Now this equation becomes L is equal to this, L is equal to 1 Henry. So because E is equal to 1, di by dt is equal to 1, 1 is equal to L into 1 is equal to L is equal to 1. So L has become 1 Henry. Look here, self inductance of a coil is said to be 1 Henry if 1 volt of EMF is induced in it when the current in it changes at the rate of 1 amp per second. So this is about the unit.